Lâm, Gia Huy và and Phương Ngọc. Okay, so let's start. Thank you. Jiu, now you can share the screen.
Can everyone hear me clearly? Is it too small?
I can hear you. It's okay, but I cannot see your screen yet.
I've just
Okay.
All right. So let's get started. Good morning, everyone. I am Hugh, and now I will present my thesis. And the topic of my thesis is study and develop generative model chatbots, and with the in cooperation with the advisor, Dr. Tan Sang. So I will first go through the outlines of the presentation today. So I'll be first talking about the thesis goals, and then I will explain some basic terminology used. I will then explain clearer about the core architecture, the core model in the my thesis, and I will show some results that I have achieved, and then draw some conclusion from it and some future work and references. So let's get started with the thesis goals by answering the three questions: why, what, and how. So why do I choose chatbot? Because chatbot is now gaining increasing attention in natural language processing, and it is also complex enough to explore the world of AI, machine learning, and deep learning. The goals, what I want to achieve in this thesis is first to rebuild a proposed dialogue generation application, spread here, and I'll analyze the shortcomings of the model and then suggest some improvements and validate those improvements. So how am I going to do this? Well, the main strategy is to find some public source code and make changes to the code and implement the improvements. So those are the thesis goals. Now I will explain some basic, some prerequisites. So the first terminology that is used a lot is the utterance. So utterance is the saying of a speaker in a conversation. The second term, generative. So this word refers to the process of generating some data we call observable X given some target Z. And generative is opposite to discriminative. So an example for this is that for discriminative process, we are given a text document and we need to find the type of that document. For example, if it's a comedy or science fiction document. And reversely, in the generative process, we are given the type, for example, comedy, and we are told to generate some data, which is documents of that type. So that is generative. The next one, recurrent neural networks. So this is a type of neural networks that process sequential data and will be used a lot in textual processing. It is able to encapsulate information from the beginning to the end into a single vector or hidden state. Some example for this is GRU and LSTM. Neural networks, I will be discussing the goal of it in dialogue modeling. So neural network is very much like a function that takes as input the observed data and outputs some predictions. And the goal of neural network is to find out the function that best, can return predictions that is closest to the ground truth by minimizing the cost function. So this f will change, which means we will change the weights in this function. So those are the basics. Now I will describe deeper about the architecture of spread, the main thing in my thesis. It is a variational framework for dialogue generation. So the architecture of spread is a combination between hierarchical recurrent encoder and decoder, HRED, and a conditional variational autoencoder. So I will be explaining these two first, and then we will come up with the full presentation of SRED. The first one, HRED. So HRED is used in modeling conversations between speakers. When this model is optimized, it will be able to generate text sequences as the responses to an ongoing conversation. I will explain the architecture and then the cost function of HRED. Cost function. First one, architecture of HRED. So it consists of 3 RNN-based blocks. The first one is an encoder RNN, context RNN, and then decoder RNN. So the encoder RNN will turn or encodes a sentence into a sentence vector. It encapsulates the information of a sentence into one vector. Here, it will update the hidden state each time a word is encountered. The next block, context RNN, it will encode a conversation or sentences to a context vector HCT. So this encapsulates the context of the conversation. Each time an utterance is spoken out, the context will be updated. The context changes. And the last one is the decoder RNN. So this decoder RNN will have its initial hidden state to be the HCT, which is the information of the conversation, and it will take input, as input the words from the ground truth or from the prediction of previous time steps, and from that it will generate words by words to form a full response. So that is the architecture of HRED. This is the full architecture when we combine the 3 blocks together. Well, this is the encoder. It updates, it encodes a sentence. And this here is the context RNN. It updates whenever an utterance is added to the conversation. And this is the decoder. It will, from the context, decode predictions. So that is the full architecture of HRED. Now, I'll talk about the cost function of HRED, what this model will try to optimize. So the cost function is negative log likelihood. So basically, likelihood gives us the sense of how probable our prediction is to the ground truth. So we want to maximize this likelihood to make it most probable. And then we have negative of the log of that likelihood. So if we want to maximize the likelihood, then we have to minimize this negative log likelihood. So that is the cost function of HRED. Right, so that is HRED. Now I will explain the second components of SRED, which is conditional variational autoencoder, CVAE. So basically, CVAE is a VAE, variational autoencoder, with just some slight modifications. So I will explain VAE first because it's a very big block. So basically, VAE is a generative model. As I've explained generative before, it is a generative model. It will be able to generate some data X when it is given a target Z, or usually referred to as latent. So this is a brief visualization of it. So the encoder will take in as input and map it to the latent Z here, and the latent Z here will be decoded back to the data X. Right. So the goal of VAE is to first generate data that best mimics its inputs. So here, the encoder will take as input here over here, and the input is mapped to the latent space, this point. And this point will be decoded back to an output, and this output must be ensured to be exactly the same. I mean, to replicate the original input as much as possible. The second goal is to maintain regularity of data generation. Regularity here means that slight changes in the value of latent z leads to slight changes of data generated. So we can see here is an example of a regular latent space. So this point from this area will be decoded into a sharp triangle like this. So as we at this point will be decoded into a circle, a rounded circle. So as we move the latent space from this point to this point, the data generated in this region will shift from being sharp to smoothen and then to be rounded like this. So that is data, regularity of data generation. Meanwhile, if a latent space is irregular, then some points in between will be decoded into meaningless data. Right, so that is the second objective of VAE. And this time, I will first discuss the cost function of VAE, and from that cost function, we came up with an architecture for the model. So the cost function of VAE, the main motivation for VAE is that for a dataset X of images or documents, we think that there might be some latent variable z that is responsible for the generation of this data. For example, z here can, in terms of images, it can it tells us about the type of subject presented by this image, for example, cars, animals, etc. So this is the latent space z, and these points are the dataset X. So there are some assumptions in this model. Firstly, they assume that the latent variable z is from a standard normal distribution. Pz is a function of this standard normal distribution. The second assumption is that Px given z is also from a normal distribution with special mean and covariant matrix. This means that the mean of this distribution is a function of f here, and f is assumed to be a function that can map from z to meaningful data x. And the covariance matrix of it is just a constant times with the identity matrix. So with the two previous assumptions, now we have known the prior Pz and also the Pz given x. So we can use Bayes' theorem to infer Pz given x. So what this means is that if we are given a latent variable z, we can use Pz given x to generate the data x. And from this Bayes' theorem, we can do the reverse flow of it, which means that if we are given a dataset x, we can infer which latent variable is responsible for that x. So here, this is the formulation, which is because we know these two already. So yeah. However, in reality, this is not possible because of the denominator of it. It comprises of a lot of other terms, and we have no information about latent z here. We don't know, it's just an assumption. We don't know how many latent variables z are there in the space, or etc. So we cannot find this term by definition anymore. We have to use an alternative technique, variation out inference. So this technique basically uses another distribution q, z given x, to approximate the true posterior pz given x. So this distribution is assumed to be normal, and its mean and covariance are functions of the data x, gx and hx. This is the mean of the Gaussian, and this is the variance of the Gaussian. It all depends on data x. So the goal is to approximate, to find out the probability that best map the true posterior distribution. So we have a formula that measures the difference between the two distributions, which is KL divergence, Kullback-Leibler divergence. So we want to minimize this. When this approach 0, the two probability distribution here will be likely to be as close as possible, as similar as possible to each other. So we run this expression through some transformation to get to this expression. So by definition, the KL divergence between the two distribution is this. It's factorized into this. This fraction over here is basically PZ given X from definition for Bayes' theorem. And then we try to analyze this. So this log is like the log of this product minus log of px. So it is analyzed into the three latter terms here. The first one is kept unchanged. Okay. So we look at the last part of it, the last term of it. This is actually a constant because log p of x is not dependent on z anymore. So the expectation of some constant will be a constant, and it cannot be optimized. So we cannot minimize it anymore. So we will negate it, opt it out from the expression. That leaves us with the three terms here. So we will flip the signs of these terms first to turn min into max. And this term over here will be changed into this. And the rest two terms here is in fact the definition of KL divergence between Q
Hello,
and Z.
I think that you should go quickly because you still have less than 5 minutes and you still talk about the background on the thing, and we would like to hear exactly what you contribute your thesis other than the whole material.
Okay.
Yeah. Thank you.
So this is the cost function of VAE. So we will map this cost function into the architecture of VAE. So we have VAE will comprises of an encoder, and the encoder corresponds to G and H, and the decoder corresponds to F. So we have to find out the three functions here that maximize this term. This term is called elbow. Okay, I'll skip this. So this is the architecture of it. So, in fact, Fred used conditional variation autoencoder. So it's just simply add a label into the architecture to better control the generation of data. So this is data generation in CVAE. So it uses another label. So, for example, if we want to generate a triangle, we will feed into the decoder the label triangle and also a variable z sampled from the distribution, and then it will be decoded into the wanted shape. Right. So spread. It is similar to HRED with two major changes. Firstly, it will separate its context into two. And secondly, it will use a latent variable z incorporated into the system. So to construct thread, we will start with HRED, and then we add VAE in and separate context, turn VAE into CVAE. So here we initialize it with HRED here, and then we add the latent variable in between. I mean, it will take as input the, this latent is sampled from the distribution modeled by the context, RNN, and the sampled latent will be used as input to the decoder and to generate responses. And we then separate the context into two. This is one status A and status B. Status A is context for person A, B is for person B. It updates whenever an utterance of that person is spoken out. And the label here is added to the input to the encoder of VAE, which is the context of the in this case. And it will also be the input to the decoder, which is the decoder RNN in the system. So that is the architecture of thread. I also noticed, as I test
Okay,
this.
you please go to the evaluation there.
Sorry. So these training, yes, the training of thread here. This is the last function of it. So it reaches to the value of about 4, and this is the visualization of the two distributions, the prior and the posterior. So it is expected to overlap each other, and this is the data, the tested data. So for a conversation, this is the true response, and this is some responses that the model come up with. This is the general response. This corresponds to the label general, and this one corresponds to the label detailed. So we control it. If we want it to respond general responses, it can be able to do so. But if we want it to generate detailed responses, and it is also able to do it. Okay. However, there's a posterior collapse in thread, and which caused the model to converge to a state where it's returning sequences with repeating tokens. Like we have EOS a lot here. Right. So I have proposed nucleus sampling to overcome that, to keep the distributions close to each other. And this is the optimization of it. We have loss reached to lower than 4, and this is how it responds to conversations. So as we can see, the response is not repeated anymore. However, it unfortunately disabled the control ability of the label. So the general response is not that general anymore, and detailed is the detailed. So now I will show the metric-based evaluation of it. So firstly, I will map a thread with the model in paper to make sure that my re-implemented model is similar to the original one. So this is the 3 metrics: average, greedy, and extrema. So they should be as high as possible. So this is my results. We can see that it is slightly worse at this metric, but it's pretty good at these 2. In terms of model improvements, I also test the thread with nucleus sampling. So at epoch 29, we can see that the training loss of it is significantly improved by almost near 1, right? And the other metrics are somewhat the same. Okay, so now some conclusions can be drawn from the thesis is that this thesis has successfully rebuilt the proposed architecture of thread, and it also suggested and validated some improvements. That is nucleus sampling. That leaves me with some future work. So I will try to use more advanced classification techniques to better assign labels to conversations, and also fine-tune hyperparameters to find the best models. So here are the references, and that is the end of my presentation. Thank you very much for listening.
Okay, thank you, Hugh. Just to summarize things, it's not clear for the committee is it for the demo. So can you again say something about the make some short demo? Say, do you have a real-time demo? So you give a topic so that the system can generate some sentences.
Yeah. So I actually have a demo code. We can test it real time. So let me share it. Okay. This is the demo code on Google Collaborate. So we have two main models. The first one is spread.
No, just make a short one.
Yeah.
To show us, let's give it a topic or something and it generate a sentence. That's it.
So we will provide it with some context first. Say, hi, how may I help you? So this time the model will answer this based on that. Oh God. Oh, this is so unfortunate.
Okay. Okay. So now we're back with you can prepare it for a few seconds. So back to the defense. So as the reviewer, so I will give my comments first, and then so I invite a question from the other members. Okay. So as a reviewer, I see that you have some improvement for the presentation, but you still spend quite a lot of time on the background. So your contribution. So if I summarize it, say you re-implement the model. Okay, you try to train the model, and you see that it can run like briefly like the original one, and then you make a small modification that slightly modify or change the result, but it not show like a big improvement. Yeah, that my comment. But you see again, your contribution in your demo is not clear for me, because the term generative chatbot is a very hot and hard keyword, because generative means we don't have a specific domain, so the chatbot must be able to respond to any kind of question from the user. It is very challenging, but it's not clear for us like how it can be achieved. Okay, so in one sentence, can you tell us how it can be achieved at generative level?
Yeah. Okay, so to achieve a generative model, it must be able to find out the latent space that is regular enough. In the slides here. So it would try to here. So this is the generative model. So in other like for example HRED, the data, the input data will be mapped to a space that is discrete, the discrete space. It is not continuous, which means that input will be mapped to a space that is discontinuous, and then these points in the latent space will be mapped to the original output, the output that best replicate the input. However, if we, in terms of a generative process, we want to generate new data from like even unseen data from that latent space.
But how?
So,
just one sentence. How it can do it?
Yeah. Okay. So for example, a sentence, when mapped to the latent space, it will be to this point, and this point, it is meaningful to the decoder, because the decoder has trained this point to generate a meaningful sentence. Oh, I forgot.
Can you just summarize it? Just one.
Yeah.
Okay.
So it will map a sentence into a discrete point in the latent space, and that discrete point is meaningful to the decoder. The decoder is trained to be able to decode that discrete point into meaningful. Yeah. So in generative, it would try to make this point to be like an area, and that area may replicate normal distribution. So because it's like it is a continuous space, so any point sampled from this area will be decoded into meaningful data. Because yeah.
Okay, thank you. That is my part. So please invite questions from other members of the committee, please. So Dr. Loan, Dr. Ng, and then finally we have the comment from the advisor, Dr. Shen. Please.
Yes, I'm here. Thank you for giving me a chance. Yes, first of all, I would like to thank for Mr. Hill. You have finished presentation, and I have some comments first. The first year you should spend very long time for presentation because and you spend a lot of time for the background similar to the Dr. Tong ideas. So in the main part, the contribution of your thesis, you can skip it and you not emphasize it for a long time, and for the another member to understand really your contribution. You should careful about that. And on the image, maybe the figures in the thesis slide, if it does not belong to you, you should citation on, yes, similar to the report. And now I have a question for you. If a sentence does not contain in your dictionary, how can you solve this problem?
Yeah. So it is basically depend on the data pre-processing. So we each sentence will be mapped to a matrix. So each word in a sentence is from the word2vec algorithm that maps a word into a vector, and that vector carries some sentiment, the meaning of that word. So for unseen words, like if a sentence that contains words that is not yet trained by word2vec, then this word2vec will assign that word with an out of vocabulary vector, and this vector will be fed into the model, and it will be processed as usual.
Yes, thank you. Yeah. Thank you for your answer. Yes.
Yeah. Thank you for
Thank you, Mr. Tok.
Yeah, Dr. Ng, please.
Okay.
Dr. Ng.
Yeah. Can you hear me well?
Yes, I can hear you.
Okay. Can you tell me what should I understand on the complexity of using the VAE?
Could you repeat that?
Okay. In one sentence. Okay. Let me detail the style of Dr. Tung. In one sentence, can you describe me what is the meaning of VAE and why and how and exactly how you apply it here, or why you apply it here?
So VAE is its role is to reconstruct data in a way that after training the model, we have a model that is able to generate any data from a regular latent space. So that is VAE, and to apply it into into the dialogue modeling. So VAE will be used to to reconstruct the ground truth. It would be used to reconstruct the ground truth. I mean, it makes response generation to be generative. In other architectures in chatbot, the latent space is most of the time deterministic. That means the latent space is discrete. So this model will make the latent space more continuous, so that sentences generated will be regular. So that is VAE applied into my model.
Okay. Yeah, I'm done.
Okay, thank you. And then Dr. Shang, please.
Okay, no, I don't have comments now. Thank you.
Okay, thank you. So that's it for the presentation of Hugh. Thank you. So everyone give him a applause. Please.
Thank you.
So next one, please.
Hello, everyone.
You can now share your screen, please.
Okay. Are you seeing me? Can I start